Hello everyone, today we are going to discuss about common collector configuration. As we discussed earlier, common base configuration and common emitter configuration. Today in this topic, we are discussing about common collector configuration. That means we are going to be common collector terminal in the circuit diagram. So let us start with biasing techniques. As we discussed earlier that there are three different types of biasing operations: cutoff, saturation and active regions. Here we can see, but in order to use transistor as an amplifier, it should be operated in active region. So we are going to use active region of operation. That means base emitter junction should be in forward bias, collector base junction should be in reverse bias. Then it behaves as an amplifier. So here let us discuss about CC configuration for NPN transistor. CC configuration circuit diagram. Here we can see CC configuration, that means common collector configuration. We should common collector terminal in this circuit diagram. So here we can see collector terminal is grounded, or we can say as taken common, and then emitter and base terminal free for input or output. So base terminal, we are using base terminal for input device and emitter for output side. So here we can see VE should be in forward bias and CB should be in reverse bias. But here we can see base and collector, it should be in first forward bias. So this is NPN. So P is at base terminal. That's why we have to connect the first polarity positive of that particular battery, because positive is P and that base P becomes similar, and that's why it is forward bias. Here we can see it is in forward bias. Now here we can see output side. First positive is connected with the collectors N type. Positive, that means P and NPNs, and both are dissimilar. N and that positive is P. So it becomes reverse bias. Here we can see this is in reverse bias. So we have to identify input voltage, input current, output voltage and output current, because we are going to discuss about input characteristics and output characteristics. So input current is IB. IB is your input current, and input voltage is potential difference between B and C, is known as input voltage, which is also known as VBC, or we can say VBB. Here VBC is your input voltage. Similarly, output current, that means IE is your output current, and output voltage is potential difference between collector and emitter, which is known as VEC. So VEC your output voltage and IE is your output current. So let us discuss about input characteristics for CC configuration. The plot of input current versus input voltage with constant output voltage is known as input characteristics for CC configuration. Here we should take input voltage at x-axis and input current should be at y-axis. So VBC is your input voltage, which is denoted in volts, and here you can see IB, which is your base current, or we can say input current, which is in microampere. It is at y-axis. Now here we are trying to start at 1.5 voltage like this, and we should take VEC is equal to 1 volt constant. VEC is equal to 1 volt because here we have to take VBE in forward bias. Then and then it becomes as an amplifier. So here if we increase VBC's value at constant VEC is equal to 1 volt, then your VBE is in forward bias. Here we can see 1.5 minus 1, its difference is 1.5 voltage. At this time, initial stage, it is not in forward bias. Then if I increase VBC's value, then and then your VBE becomes in forward bias. Another value VEC is equal to 2 volt. At this time, here we can see if you increase VBC value, then your VBE becomes forward bias. So this is the input characteristics of common collector configuration. Now let us discuss about output characteristics for CC configuration. Now output characteristics is also VI characteristics for CC configuration, but we should take output voltage and output current. Output voltage should be on x-axis and output current should be at y-axis. So here we can see at x-axis VEC, because VEC is your output voltage and IE is your output current at y-axis, which is in milliampere. Now this is the output characteristics. So it is divided into 3 different regions: cutoff region, saturation region and active region. So let us discuss with cutoff region. First, if I apply IB is equal to 0 microampere, IB is your input current. If your input current, or we can say base current, is equal to 0 microampere, at this time your output also is 0. So IE is 0 and then your IC is equal to reverse saturation current. So this region is known as cutoff region. Here you can see the highlighted area is known as cutoff region. Now if I increase IB's value 10 microampere, at this time you will get different IE in milliampere. So IB is equal to 20 microampere, IB is equal to 30 microampere, and then IB is equal to 40 microampere. You will get different values of IE, but it is in milliampere. We can see this characteristics is similar to the common emitter configuration, because here there is no difference, no major difference between IE and IC. I already told you that IC is total currents 98%, is approximately IE is equal to IC. That's why you will get same characteristics, same output characteristics as we discussed in CE configuration. Here we can see straight linear line which is indicated saturation region. So this is saturation region and this one is your active region. So as we discussed in this characteristics, 3 different types of region: cutoff region, saturation region and active region. Its application is impedance matching circuit. CC configuration for PNP transistor. Here we can see this is the PNP transistor. The battery's polarities are changed, or we can say inverse, compared to the NPN transistor. Here 2 different types of batteries we can see, both polarities are inverse, and that becomes your PNP transistor. So it is in forward bias and it becomes in reverse bias. Now transistor current gains, as we discussed in our previous topic, gain, that means output current upon input current. There are different types of gain: CV current gain, which is indicated as alpha; CE current gain, which is indicated beta CC current gain, which is indicated as gamma. Alpha is equal to IC upon IE, beta is equal to IC upon IB, and today we discussed about CC configuration. So its equation gamma is equal to IE upon IB. And one more important equation, as we discussed earlier, IE is equal to IB plus IC. That means IB is total currents 2% only and IC is total currents 98%. So in today's lecture, we discussed about gamma is equal to IE upon IB. So that's all for today's lecture. Till then, keep learning, keep reading. See you soon in next coming lecture. Thank you.